Alright. So first thing first, I am starting to grade the midterm for this class, so it won't be very long before it's all done. So I have got one question already fully graded. The second one is in progress. So yours may be graded or may not be graded for the second question. So I'm in the process of doing it. We do have one homework assignment, which is called Array 1. So you might want to get started with this one as soon as possible, just to make sure that you don't have any big questions. If you have questions about Array 1, you can bring those on Tuesday, so we can talk about that. Right? It's due in a week. It's due in a week, next Thursday. All right? So what we'll do today is to continue what we talked about the other day, which has to do with short-circuited evaluation. So what we'll do is I'm going to use LibreOffice to kind of show you the code that had a problem before, and then we'll fix it, using two ways, okay? Two possible ways to fix that problem. And in terms of the notes on Moodle, we are now moving on to topic 6. So topic 5 is pretty much done, even though the homework assignment is in topic 5. We're actually moving on to topic 6 now. So the first topic in topic 6, first topic or the first link in topic 6 is short-circuited Boolean operators. So we'll start with that today. All right. So I'm going to give you a faulty algorithm, and then we'll fix it. The faulty algorithm, looks like this. We're searching for a particular value in an array, but we'll do it in a way that it's not going to work. Okay, it will work in some cases and not work in other cases. We use variable I to store the index, and then we'll say while what I'm looking at right now, or the array element that I'm looking at right now, does not equal to the value that I'm searching for, and I is less than bar a bar, which means we have not gotten to the end of the entire array yet. We'll just go ahead and add 1 to I gets I plus 1, and while. When we get out of the loop, we'll use a variable found to remember, did we get what we were searching for? So found would get, in this case, I is less than bar a bar, and that's my algorithm. Now this algorithm works in some cases, but it doesn't work in other cases. So we'll take a look at how it works and how we can break the algorithm. Are there any questions about the algorithm itself? I think we came up with this algorithm last time. Remember, we derived the algorithm step by step, and this is what we ended up with. And I said, it's not going to work because of the way we arrange the comparisons inside the conjunction. So we'll go ahead and trace it and find out, okay, but exactly why is it not working? Right? So the way it's not working is like this. So we have line number, we have I as our variable, and we have K, which is the value that we are searching for, and then we have array A. In this case, I can just make an array of 2 items, just so that we can save time. We don't have to go through all the iterations. And in the first test case, we'll have A bracket 0 has a value of 6, A bracket 1 has a value of 3, and the value that we are searching for is in the array. Okay, so it's 3. I starts with an unknown value, and that's our precondition. So I'm gonna line up everything, and comments needs to be a little bit wider because the condition we are evaluating takes up more space this time. Okay, line 1 starts with I getting 0. On line 2, we evaluate the condition. A bracket I is A bracket 0 because I has a value of 0 at this point. K has a value of 3. 6 does not equal to 3 is true. And then we have and. I is 0 at this point. Bar a bar in this case is 2. 0 is less than 2 is also true. True and true is true. Are there any questions about this condition? And then we move on to line 3. We add 1 to I. I goes from 0 to 1. We go back to line 2. A bracket I is now A bracket 1. A bracket 1 has a value of 3. K has a value of 3. 3 is different from 3 is false. I is 1, 1 is less than 2 is true. So this time we have false and true, which is false. So that will get us out of the loop. We end up on line 5. On line 5 we have to, we need a column for found. So found starts with an unknown value as a precondition. So by the time we get to line 5, we have to evaluate the right-hand side. The right-hand side is just I is less than bar A bar. I has a value of 1 at this point, bar A bar is 2, 1 is less than 2 is true. So true is the value of the right-hand side of the assignment. So found as a variable is going to store the value of true. And then we get to post, no problem. The algorithm does not break anything. It came to the correct conclusion that the value that we were searching for, which is 3, does exist in the array. Not a problem. Are we doing okay with this trace? Okay. So if this trace is okay, there's no problem, then what can possibly be the problem? So let's go ahead, let me go ahead and copy and paste this into another sheet, and then we'll trace the other one. But this time, instead of looking for 3, I'm going to look for 4. And then we'll start the entire thing all over from the beginning. On line 1, we initialize I to 0. On line 2, we evaluate the condition. No big deal, A bracket I is A bracket 0 because I equals to 0 at this point. It has a value of 6. 6 is different from K, which has a value of 4, is true. The second part is comparing I, which is 0 at this point, to bar A bar, which is 2. 0 is less than 2 is also true. True and true is true. We go to line 3, I gets incremented to 1. We get back into line 2. A bracket I is A bracket 1, which has a value of 3. K has a value of 4. 3 is different from 4 is true. I is 1. Bar A bar is 2. 1 is less than 2 is also true. True and true is true. We go to line 3. We add 1 to I. I is now 2. We get back onto line 2. And we have a problem now. Okay? Because what exactly is A bracket 2? There's no A bracket 2 in the entire algorithm or in the trace. So that's why we have a problem. Because we are now, so depending on the programming language, one of 3 things can happen. One, in C and C++, it will consider column G as A bracket 2, because whatever is adjacent to A bracket 1 has to be A bracket 2. But that's obviously not the case, because the array only has 2 elements. So in C and C++, it will just use column G as if it is A bracket 2, but it is not A bracket 2. So that operation is wrong, because it's comparing to the wrong thing and not even know about it. Okay? In Visual Basic, it will give you an error message, and it will basically say on line 2, you are trying to access an array out of bound, and the program will stop, give you the line number that has a problem, and that will be the end of it. Okay? That's actually the right answer to this problem. In PHP and Perl, both scripting languages, when you try to access an item in an array that does not exist yet, it will make the array large enough that it starts to exist. So right now, at this point, the array will now start to have A bracket 2 in existence. So bar A bar becomes 3. Okay? And that becomes an infinite loop, because as long as what you're looking for is not a default value of an element in an array, A bracket I does not equal to K will never match. But I is less than bar A bar is also going to be true all the time, because the array is getting bigger with each iteration. So it becomes an infinite loop, and it will only chew up all the memory in your system, and then it will crash because it runs out of memory. Okay? So in either case, in all 3 scenarios, this is something that you do not want to encounter when you're actually running a program. So how do we fix this problem? One way to fix this problem is to change the algorithm itself, so that we do not evaluate anything that has the square bracket or the indexing operator unless we know for sure that the index is within the correct range. Okay. So there are ways to do this. Okay. One way to do it is to say I gets 0, and we also make use of the variable found from the beginning in this case. So what we do is we say, let's say the element is not in the array unless it is proven otherwise. So until we actually make a match between an element with k, we basically say it is not found. Okay, and so that's why we initialize the variable found to false in this case. The loop is going to be structured a little bit differently, because what we can do is now we can say if it is not found, because if it's found we're done, we don't need to continue the loop anymore. As long as it is not found and I is less than bar a bar, we do the following. In other words, as long as we have not found the value that we were searching for and there are additional elements that we can look at, we'll do the following. In the loop this time, the first thing we do is we look at found and say, well, let's change found to whether a bracket I does equal to k or not. Okay. Now this time it is perfectly okay to refer to a bracket I in this case, because unless I is still less than bar a bar, we cannot get to this point because of the structure of a loop. Is that making any sense? The condition of the loop on line 3, found being false and I is less than bar a bar, guarantees that on line 4, when we refer to a bracket I, that I is still a valid index into the array. Is that okay so far? Okay. And after this, we can say I gets I plus 1. You can use a conditional statement and say that you only increment I when found is false, but that's really not needed because we just need to know whether it is there or not. So as long as you're not relying on I to indicate where the value is, this will work just fine. All right, so we'll go ahead and trace this algorithm using the same 2 test cases that we had used before, and then see how this particular algorithm will do things a little bit differently. The first one is when we do have the element in an array matching the value that we were searching for. Okay, so we'll do exactly the same thing, starting the search from the beginning. I gets initialized to 0 on line 1. On line 2, found is initialized to false. On line 3, we have the loop here, or the condition of the loop to evaluate. Found is false, not found is true. I is 0. 0 is less than 2 is true, so we have true and true, which is true. We go to line 4. On line 4, it looks kind of funky, but it's not, because it's just an assignment statement. With any assignment statement, we evaluate the right-hand side first. Whatever the value of the expression is, we use it to update the variable on the left-hand side. In this case, the expression on the right-hand side doesn't give you an integer value. It gives you a Boolean value. It gives you a value that is either true or false, which is perfectly okay. A bracket I at this point is a bracket 0 because I equals to 0, and k has a value of 3. A bracket 0 has a value of 6. Are they the same? Nope, they're not the same. So the result of the comparison is false. So we're going to store exactly that value into found, which is false. We move on to line 5. We add 1 to I. I goes from 0 to 1. We go back onto line 3. Found is false. Not found is true. I is 1 at this point. 1 is less than 2 is true. So once again, we have true and true, which is true. We go to line 4. On line 4 this time, a bracket I is a bracket 1. A bracket 1 has a value of 3. 3 equals 3 is true. So found is now updated to a value of true. We go to line 5 again. We add 1 to I. I goes from 1 to 2. And we go back to line 3. But you know what? There's no problem in this case because found is true, not found is false. I is 2. 2 is less than 2 is false. So now we have false and false, which is false. But it doesn't cause us the problem that we had before because line 3, the condition of the loop, does not have any indexing operation. So we don't have to worry about getting to a part of the array that does not exist on line 3 in this case. Is that making any sense? And that's why we can solve the problem. Because after line 3, we just get to post. And by the time we get to post, if you look at the variable found, it has the right conclusion. The value that we were searching for, which is k, does exist in the array. That's the conclusion. Not a problem. Well, if that is not a problem, what about the other test case in sheet 3? Okay, this is the one that broke our algorithm before. So let's go ahead and trace this one, but using the new algorithm, and see how well the new algorithm can deal with this particular test case, where the value that we were searching for does not exist in the array. Line 1 initializes I to 0. Line 2 initializes found to false, just like with the previous one. Line 3 is evaluating not found. Found is false, not found is true. I is less than bar a bar is evaluating 0 is less than 2, which is also true. So now we have true and true, which is true. We go to line 4. A bracket I is A bracket 0, which has a value of 6. 6 equals to 4 is false. We go to line 5. We add 1 to I goes from 0 to 1. And we continue execution at the beginning again, which is on line 3. Found is false, not found is true. I is 1, 1 is less than 2 is true. Once again, we have true and true, which is true. We go to line 4 again. On line 4, we evaluate the right-hand side. A bracket I is A bracket 1. A bracket 1 has a value of 3. We compare 3 to K, which has a value of 4. 3 equals 4 is false. So once again, we store false into found. We move on to line 5. Incrementing I from 1 to 2, we go back to line 3. Not found is true, because found is false. Not found is true. And I is 2 in this case. 2 is less than 2 is false. So this time we have true and false, which is false. We get out of the loop. We get to post. Not a problem. We come to the right conclusion because found remained false the entire time. Is that okay? So this is one way to solve the problem. Go ahead.
So it's okay that I equals 2 as long as you're not looking at A.
Exactly. Yeah, because if you look at I as a variable by itself, it is no different from any other variable. It's only when you use I or any expression that gives you a value that is greater than bar a bar minus 1 as an index into array A, then you have a problem. So I can have 20,000, but as long as you're not trying to use it as an index, who cares? That's a good question. So I itself has no special value. It's only when it is inside the square bracket that you have to be careful. All right. Are there any questions about this particular case? Yep.
You just said it's only appropriate to use it when it's a very. I didn't understand. I want to understand. Like it's almost there. But
Okay. Okay. So the thing about I as a variable is it is not special. I name it I for index, but when you look at it as a variable, it is just like any other variable that we have talked about, like W, X, Y, Z, and so on. It's only when I or any expression is used inside the square bracket, when we use the expression as an index into an array, then you have to be careful, because if that expression gives you a value that is either less than 0, like -5, or greater than bar a bar, like in this case 3, 4, and 5, then we have a problem because we're trying to access an element that is not in the array. But as long as that expression is not inside the square bracket, hey, who cares? All right. So this algorithm does solve the problem by making use of the found variable, so that when we are evaluating the condition on line 3, we don't have to directly look at a particular element in array A. Therefore, we avoid the problem. Okay, it has to do with not using the square bracket operation when we are on line 3. Okay, but it is kind of cumbersome because it's longer for one thing, and we have to keep updating the variable found the whole time. So it's not efficient. It is kind of cumbersome. So we would like to have another solution to this problem. So the other solution to this problem is almost the same thing as the original algorithm. So I'm going to switch back to the original algorithm here, and I'll just copy and paste it. And in this case, I will create a new algorithm based on the one that did not work by changing the ordering of these two things inside the conjunction. So instead of comparing A bracket I to K first, I'm going to compare I to bar A bar first. Okay? Now that by itself is not going to solve the problem. So I have to say that in this particular case, we are also going to use a convention called short-circuited Boolean evaluation, okay? Or otherwise known as lazy evaluation.
Mm-hmm.
What it does is it is always going to evaluate a conjunction or a disjunction from left to right. Okay? So we cannot change the order of the two sides anymore. On top of that, it is also stating that as soon as you come to a conclusion for the entire expression, you stop. For a conjunction, if the left-hand side is false, you do not evaluate the right-hand side, because false and whatever is always false. Doesn't matter what the other side is. For a disjunction, for or, if the left-hand side is true, you don't evaluate the right-hand side, because true or whatever is always true. Okay, so that really is the convention of short-circuited evaluation. So with that convention, and by rearranging the comparison using this new method, we can also solve the problem. Okay, so we'll take a look at this particular algorithm, and we'll trace all the same traces as before, and then see how this one will behave differently. Yep.
Is there a way to notate that in an actual algorithm?
No, there's no way to denote that you're using lazy evaluation. If you really want to emphasize that your conjunction is lazy or your disjunction is lazy, I suppose you can say lazy and or lazy or. But otherwise, no programming language that I know of has a special notation for using short-circuited evaluation. In Visual Basic, they have a notation for the non-lazy version of AND and the non-lazy version of OR. The non-lazy version of AND is AND also, and then the non-lazy version of OR is OR else. So in that case, it guarantees to evaluate both the left-hand side and the right-hand side, regardless of the values. It does not come up a lot, but there are situations where it becomes important whether you evaluate both sides or not. In C and C++, there's just no way to denote that. I mean, it just stops evaluating when one side is determining the entire outcome. That's a good question. All right, so let's go ahead and trace this algorithm. This one was not a problematic one to begin with, okay? But we'll trace it anyway just to make sure that this is still correct. So on line 1, I gets initialized to 0. On line 2, we evaluate the condition. I is 0, 0 is less than 2 is true. Well, can we stop here? I mean, the left-hand side is true already. This is a conjunction, so if one side is true, the whole thing can still be false. So we have to evaluate the other side. A bracket I is A bracket 0. A bracket 0 has a value of 6. 6 is different from 3, which is the value of K is true. We have true and true, which is true. We go to line 3, we add 1 to I goes from 0 to 1. We go back onto line 2. I is now 1. 1 is less than 2 is true. We cannot conclude the result of the conclusion just yet. So we have to evaluate the other side, the right-hand side of the conjunction. A bracket I is A bracket 1. It has a value of 3. K also has a value of 3. 3 is different from 3 is false. True and false is false. So we get out of the loop early. Now we get to line 5. On line 5, we have to update the variable found. The expression that we use to update it is I is less than bar A bar. I is now 1, bar A bar is 2, 1 is less than 2 is true. So that is what we are going to store in found. And then we get to post. We're done. All right. Are there any questions about this particular case? It worked before, and it continued to work without a problem in the modified algorithm using short-circuited evaluation. Not a problem. All right, so let's take a look at the one that gave us problem in the past. I think that's in sheet 6 here. And we can just copy and paste the problematic one. Stash it. Okay, I guess I did not. I did copy it. It's not responding. Yesterday, halfway through my mobile programming class, we had a power fail.
What time was that? Time?
It must be around 10 o'clock, maybe 9:30, 9:45 or so yesterday. 9:30, there was a power fail. Yep, so there was no light in the classroom, the projector was down, the computer was down, and I was still teaching my class without any interruption.
Wait, was it during the evening or in the morning?
Hmm?
Oh, in the morning.
In the
Also,
morning.
Say, it was
Yep.
in the evening, that'd be a different story.
Oh, how so?
No power at all. Oh, phones. It'd be dark nerves.
Oh, okay. But now we have a slightly different problem. You know, the I just I just press Control V and you can see that it's not responding. And to me, sometimes this is a harder problem to fix because it's not like completely gone. It's just being non-responsive for apparently no reason. I might have to. Oh, come on. Okay, well, since it's doing this, I can show you what I did in my previous class. Yesterday, I pulled out my flashlight because the room was completely dark, right? Because there's no light whatsoever. So my little flashlight, turned out to have enough. It was throwing out enough light to actually, on the whiteboard, and then I just picked up my dry board marker and continued teaching until power was restored. And there was also screen recording the entire time. Even though the computer was down, one of my students just used his Samsung Galaxy S4 to record the portion that was done on the actual whiteboard. And I posted it onto YouTube as well. Because I want to show my dean that, yes, we are making the best out of all the resources possible available to us. Okay. Problem with the software.
Maybe too many tabs.
No, there are only 10 tabs. 10 tabs is nothing to a spreadsheet. Uh-oh. It won't even start. Okay, now it's starting. It wants to restore, say, recover. Okay, let's give it a try.
Worth a shot.
Well, usually it does a pretty good job doing it. Okay, I think it restored some parts of it, but not the other parts. So we lost the program that had the lazy evaluation or short-circuited evaluation. That's okay. I can just type it again. That's not going to take up too much.
Have a copy?
Hmm?
Can you just paste it? Maybe a copy of the book?
I probably don't.
You were copying something else that time.
Yeah, that's okay. Do this. There we go. The only modification is really just reversing the order of the comparison. All right. So I'm not going to redo the trace of the one that worked. I'm going to redo the trace of the one that did not work, which is this one here. And open a new window for the trace, and have one to look at the algorithm just like before, and trace from the beginning. All right, so now we're back to square one of the trace of the test case that did not work before we use a short-circuited evaluation and flip the order of the condition. So let's take a look at this one. Just make it a little bit bigger, so this way we can look at the algorithm a little better. Line 1 initializes I to 0. Line 2 evaluates the condition. I is less than bar A bar is true because I is 0, bar A bar is 2, 0 is less than 2 is true. With a conjunction, that doesn't tell me the final result, so we have to look at the second condition as well. A bracket I is A bracket 0 because I has a value of 0. We compare that which A bracket 0 has a value of 6, K has a value of 4. 6 is different from 4 is true. We have true and true, which is true. We go to line 3, we add 1 to I, it goes to 1, we go back onto line 2. I is now 1. 1 is less than bar A bar, which is 2, is true. A bracket 1 has a value of 3. K has a value of 4. 3 is different from 4 is true. We go to line 3, and it increments I to 2. We go back into line 2. I is less than bar A bar is false because I has a value of 2. Bar A bar also has a value of 2. And this is how I denote, short-circuited evaluation. I only evaluate as far as I need to come to the conclusion of the entire conjunction. So from now on, unless I tell you that a conjunction or disjunction is not short-circuited, you will have to follow the same convention. Only evaluate a conjunction or disjunction as far as you need to find out what the answer is. Are there any questions about the mechanism of short-circuited evaluation, or how to represent it when we come to a trace?
When you say as far as you need to, you mean, can you keep going? Is there a...
Oh, well, you mean for the expression itself, for the conjunction expression, or for the entire algorithm?
Well, when you say only goes as long as you need to,
Right.
how would we go further if it was...
We do not have to evaluate A bracket I does not equal to K anymore, because with a conjunction, if the left-hand side is false, the entire thing is already false.
I see.
So there's no need to evaluate the right-hand side. Yep,
Okay.
go ahead.
So will we always be using the short circuit Boolean evaluation, and so we're not going to have to use like the not found what we're using?
That is correct.
for,
Yep. Because it is a part of the language specification in C and C++, as well as Visual Basic. In fact, all programming languages that I know of, that are popular at this point, so that would include PHP, Perl, Python, and so on and so forth, Java, they all use short-circuit evaluation. The only programming languages that does not use a short-circuit evaluation would be older programming languages like Pascal, COBOL. I'm not 100% sure about SQL, but in SQL it's a little bit different because it typically does not run into problems like what we are running into here. All right, so we'll go ahead and get to line 5 because the program is not done yet. We have to get to line 5. On line 5, we will I is 2, bar A bar is 2, 2 is less than 2 is false, and that's what we are going to store in the variable found. And then we get to post, and the algorithm is now okay. It does not get into the problem that we had before, and found has the right conclusion. Do we have any questions about this trace? Go ahead.
So this is what you would put instead of trying to basically break the trace by adding an extra bracket?
It does not break the program because the bracket operator is on the right-hand side, and the left-hand side becomes quote-unquote a guard condition for the right-hand side, because the left-hand side says I is less than bar A bar. So if I is not less than bar A bar, which means I is no longer a valid index into the array, it becomes false. The left-hand side becomes false, and using the short-circuit evaluation mechanism, we don't even bother with the other side. All right. So that basically finishes this part of topic 6, which is short-circuited Boolean operators. And now we are moving on to searching in a sorted array. Now, when an array is sorted, we can still use the same algorithm. If I go back to the algorithm itself, just hold on 1 second here. So if I use this algorithm on a sorted array, it still works okay, right? It works on an unsorted array, but it will also work on a sorted array. But if you're working with a sorted array, we can probably do something to make this algorithm slightly more intelligent. Okay, the slightly more intelligent part depends on how the array is sorted. Assuming the array is sorted in a non-decreasing order, which means A bracket 0 is less than or equal to A bracket 1, A bracket 1 is less than or equal to A bracket 2, how can we optimize this algorithm and get out earlier? Okay, so let's go ahead and take a look at this algorithm. make a new one out of this one.
Is greater than K.
And then we say, how can we make this more efficient if we know that the array is already sorted? Yep.
If A bracket I is greater than K, then get out.
Okay. All right. So that means as long as it's less than, we should still stay in the loop, right? But then found needs to be a little bit different because this time we have ways to get out earlier. So that means when we look at found, we need two things to confirm that something is actually found. That's the first indicator, but we also need to confirm that A bracket I does equal to K. Okay, so this algorithm is optimized, slightly optimized, to search in an array that is already sorted in a non-decreasing order. Okay. Let's see why it makes sense. We'll just use a concrete example to find out why it makes sense. So we are looking at an array that is already sorted. So let's say we have 3 items in the array, and the values are 1, 4, and 7 in this case. Let's say we are searching for something that does not exist in the array. So we are searching for 3 in the array. We compare 3 to 1, doesn't match. Okay, so we have to move on to the next item. Now, if 3 does not match 1, does it say anything about all the other items cannot match 3? No, because 1 is less than 3, which is no guarantee that the next item cannot be less than 3 also, right? Okay, so the next item is to compare 3 to 4. They do not match. But can I exit now?
Yes.
I can exit now because 4 is greater than 3, but because the array is already sorted, that also means anything after that will also be greater than the value that we are searching for. There's no need to compare anymore. So that's why, to stay in the loop, we want to make sure that whatever we're comparing to is actually less than the value that we are searching for. Because if it's greater than or equal to, we should get out. Now, to make the conclusion of whether we actually found the item, then we have to have 2 things to do, because now we can exit early. The first reason to exit, there are 2 reasons to exit now. When we exit, A bracket I can be greater than or equal to K. So that's why in the second, on line 5, to determine whether we actually found the item or not, we have to first see whether I is less than bar A bar. Because if we are searching for 9 in this case, then we would get to the end here, and I would be 3 in this case, and it would fail the first condition, and the entire conjunction would be false to begin with. On the other hand, if we're looking for 3, then we would be getting out of the loop early. I would still be less than bar A bar, so we need to rely on the second condition, A bracket I equals to K, to tell us, okay, we know that we got out early, but did we actually get out early because we found the item, or only because whatever we're searching for is already less than the item or the value of the item that we were looking at in the array? Okay, so it's a slight modification to make it go faster. On the average, assuming the value that I'm searching for in the array is evenly distributed, how much time am I saving using this optimization? About 50% of the time, right? Because sometimes I look for something that's really small, so I can use this to kind of shortcut and saves me a lot of time. Other times I'm looking for something that's really huge, so it doesn't offer any saving at all. So on the average, I'm saving about 50% of the time compared to not using this optimization. Okay, 50% is not a small number, but it's not really that good of a number either. Okay, I'm going to erase this, and I will ask you a question. The world population is about 7 billion at this point. Okay, so if I have an array with some kind of ID or some kind of attribute of every single person in the world, and it is already sorted, if I want to search for a particular item, how many comparisons will you need in order to tell me that this item does not exist in the array? This person does not exist. Hmm? Well, okay, let me think of a way to sort, to identify each person. has to be a unique ID of some kind. Okay, so I'll just assign each person a unique ID. Okay, so you have a unique ID, I have a unique ID, everybody has a unique ID. The array, is using just the unique ID. So we have 7 billion unique IDs, in the array. So here comes, a number, and I want you to confirm, is this an actual ID in this entire array? That's the question. Okay. So let's say the number that I gave you is actually not one of the 7 billion items in the array. The question is, how many comparisons do you need in order to confirm that it is not in the array?
I think 10 for every digit.
10 for every digit. So you're basically using a way to index into the digits. But since the array is sorted, it does not necessarily lend itself to that sort of lookup mechanism, because it can be sparse. You can have, like 0, 0, 0, 0, 0, 0, 1, and then the next number is like, 9999654, whatever, right? So that means, you cannot use it's called a radix type of a lookup, because you're using a digit to find out, okay, now we narrow down to this part, we narrow down to this part. But with an array, you don't know where it starts. Okay, there's no easy lookup to find out, okay, where does, all the numbers starting with 6 begin? So there's no easy way to apply what you just said. Okay. How many comparisons do we need? If we store the numbers in a certain way, then yes, that mechanism we may be able to use it.
Well, if it's random, wouldn't it be 7 billion?
It is sorted though. The items in the array are still sorted.
No, but if you, how are they sorted?
They're sorted by the ID, because an ID is a number, so we can sort those numbers.
It's non-decreasing.
Non-decreasing. Well, it doesn't matter. It's sorted in one particular order. Yep.
You need 2,
Well, we need a little more than 2.
because you don't want brackets to be lower, and then you want another one to be higher, and that way you can get
No, we need a little more than 2. Okay, I'll give you the answer, 33. Okay, 33 comparisons for an array of 7 billion items. If world population doubles again, how many comparisons do you think I will need?
66.
34. If we conquer the entire solar system, and people start to live, on Europa, and so on and so forth, and we have 28 billion people, how many comparisons would I need?
35.
35, exactly. Okay. So how do I manage a search algorithm that is that efficient? Well, it's called binary search. What binary search does is it looks at the entire array. So let's say these are the small values, and these are the large values in the array. So it is sorted in this order. So the way it works is I do not start here, I do not start here. I start right in the middle of the entire array. In other words, I compare my key, what I'm searching for, with the item right in the middle of the entire thing. There are 3 possible outcomes, right, when you compare numbers. The first outcome is equal, which is lucky, right? What I'm trying to look for is right here. The first item that I compare to is the one that I'm looking for. Unlikely to happen, but sometimes it does. But more likely, it will be one of these 2 other cases. It can be less than, or it can be greater than. Okay, in the case of the K, key is less than the item that I'm looking for here, what is it telling me? If K is already less than this item, and these values are all larger than this particular item, I can rule out the bottom half of the entire array, because all of those values will be greater than the one that I'm looking for. So now I only have 1/2 of the array, approximately 1/2 of the array remaining to search in. What if it's greater than? What is the value that I'm searching for is greater than the value that I'm looking at, which is right in the middle of the array? The opposite is true, right? Because if K is greater than this number to begin with, it's going to be greater than the first half of the entire array. So I can only find, if it is there, I can only find it in the second half of the entire array. So what do I do with the second half of the array?
Cut it in half.
Same thing, find out what is in the middle, do the comparison, throw away one or the other half, okay, and then do the same thing again. So each time I compare, I eliminate one half of the remaining possibilities as candidates. And so the question becomes, how many times do I have to divide 7 billion by 2 until I get to a number that is smaller than 1? Because by that time, I know the item does not exist in the array. Is that making any sense? Okay. So it's called binary search. It is a very efficient way to search for an item when the array is already sorted. Okay? All right. Why is that important? Why is it important to find algorithms that are efficient? Well, before you guys answer that question, I'm going to bring up a little comic strip that I found last year. And for whatever reason, I did not put it into this class, but it was in the other class. So I'm going to bring up the page from the... Yeah, I mean, why is it so slow? That is just weird. I mean, it's not just browsing, but everything else is kind of slow too. It's in topic 6, and there's a URL in topic 6. Okay, so this is the link. It's kind of funny. Okay, so let's see here. I'm not going to use the mouse pointer because if I hover the pointer over, it's going to show me. It has a little caption. Okay, so here's me, yakking away with all the theoretical stuff. You can see all the conjunction symbol and stuff like that. So I'm yakking along and saying, thus, for any non-deterministic Turing machine M that runs in some polynomial time Pn, da 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 da. And for those of you who are moving on to a computer science program at a 4-year university, guess what? You will get to that stuff. Okay, so that is actually in your future if you want to be in a computer science program. And this guy here, unlike all the other guys with a notebook, a pencil or something, he has got nothing on his desk. And he's saying, what the man, I just wanted to learn how to program video games. So he's thinking all of this theoretical stuff has nothing to do with video games. Okay, well that may be the case, that may not be the case. How can this person know whether it applies or not when he's not even into video games already at that point? I mean, if he is in his, if he or she is in his 70s, retired from the gaming industry, that person will be qualified to say, oh, this stuff does not relate to gaming, because in my 30 or 40 years of experience of writing games, being a successful game programmer, this stuff never popped up at all, right? But how can this person in the class, make that conclusion? It'll be pretty hard to make that conclusion, I would say.
That's sufficient.
Okay. Yep. So what I'm going to do is I will continue with this discussion here, using binary search, okay? And I want to tell you why it is important, okay? Because it seems like, yeah, it's efficient, but why is it important? What if I use linear search and the other person uses binary search? Does it make a big deal? I mean, well, it does make a big deal, okay? Because let's say, okay, most of you by now have recognized that the computer industry or high-tech industry tends to be cyclical, okay? And not only is it cyclical like all other industries, it goes up and down in huge magnitude. When it's good, everything is good and people making gobs of money. When it's down, everybody gets laid off, okay? If you look at 2000, okay, shortly before the dot bust was the boom. When it was booming, it's really booming. It pushed all the non-high-tech industries out of San Francisco, just like what it's doing right now. Okay, so if you go to San Francisco, there are no, a piece of shops cannot afford the rent anymore. Okay, because all these high-tech companies are moving in and they have gobs of money, and they say, okay, we want to rent that space for this much money, and the pizza shop is only offering this much money. What is the landlord going to say? Yep, exactly. Now, if all the people in San Francisco are in the high-tech industry making this much money, think about the apartments.
Oh, fine.
Okay, so the apartments are now, basically we have, the entire horde of these high-tech workers making, six figures trying to move into these apartments, and then the apartment had, let's say retired people, making, this much money, just barely affording the rent. What would the landlord do? Well, in San Francisco, they have rent control. So you cannot jack up the rent, beyond a certain percentage per year. So what would you do if you are a landlord?
Start checking it up each percentage per year.
Well, you can only
So-
jack it up legally up to
Yeah.
a certain point. So what you do is you sell your apartment complex. Because when you sell your apartment complex, that nullify all the rental agreement with your existing, tenants. So the next guy who bought your apartment complex, which can be someone that is related to you, can come in and kick everybody out. So that these six people making six figures can move in, and you can jack up the rent to the appropriate level.
That's unethical. That's smart.
It is unethical, but it's being done. Unfortunately, it is being done in San Francisco because they wanted to get these people in the city. It's not only affecting rental with apartments. It's also affecting public transportation. Even Munich is affected because guess what? Google, Facebook, and all the other big companies in the Bay Area, they have their own shuttle service. They run their quote unquote their own bus line to these high-end apartment complexes to pick up the employee, so they don't have to stop all over the city. They just go straight to Google headquarters. It's happening right now in San Francisco. So right now it's in the dot boom stage, and at some point the bubble is going to burst and it will go into the dot bust cycle. So anyway, the whole point is, it will get into the dot bust, cycle. So all of these people will get fired from the company, and then bad things will happen. So let's say that we are now in a down cycle, and in the company it's only between me and Pat as the only remaining developers. Okay, and the company says, we can only afford to have one developer in this company. Okay, so either I have to go or Pat has to go. So the boss, is really sick and tired of our discussion, argument, and I'm trying to promote myself. Pat is trying to promote himself or herself, and there's the boss is saying, okay, enough argument. I'm gonna settle this with a competition, with a programming competition. Okay, I'll give you an array, to search, and whoever can do that search, quicker, is going to come out ahead and stay with the company. Okay, sounds fair? Okay, and except the boss is not saying is not mentioning anything about the number of comparisons. The boss is saying, I have a stopwatch. Okay, so whoever can come up with the answer earlier is going to will win the game and gets to stay with the company. I'm at a slightly disadvantage here because I joined the company in the late 80s and I never upgraded my computer. So I have a 486 computer on my desktop in my office. Okay, so here is Pat with his 486 processor. Pat, on the other hand, joined the company just 3 months ago. Okay, and so Pat is running a computer with a latest and greatest i7 processor. Okay. So how much faster is an i7 processor compared to the Intel original 8486 processor?
Oh, sure.
You don't have to look up any special technical document because I will give you a way to do the estimate pretty quickly. Okay, it's called Moore's Law. Moore's Law. Okay. Moore's Law says one thing. What does it say?
That every 18 months, processing power will double.
Yep, go ahead.
Isn't it every 2 years the processing power of computers will double?
It's actually 18 months. Every 18 months. Okay. So with Moore's Law, all I need to do is to have a reasonable estimate of when the 486 processor came out. which is 1989, which is before many of you were born. The i7 processor will just consider latest and greatest version, which is 2013. How much time has passed from 1989 to 2013? 24 years. Okay, 24 years. So Moore's law says doubling 2x every 18 months. And every 18 months is the same as every 1.5 years. How many 1.5 years are in 24 years? 16. Okay, so there are 16 cycles of 1.5 years in 24 years. Okay, so that means, does that mean Pat's computer, just using this estimate is 16 times faster than mine? No, it's 2 to the power of 16 the speed of mine. Okay, so that's about 65,000 times. Okay, I would call that a slight advantage. Just a little bit here. Okay, so as a result, Pat knows that too. So because Pat knows that, he or she thinks, I could never tell whether it's a he or she. So Pat says, well, I'm gonna beat your time anyway. So I'm gonna look up Wikipedia, find the easiest search algorithm to implement, and I'll just kind of sit back and enjoy my continued employment when tech is scrambling, pack up my boxes and try to find my next job. But you know what? Because I know I have taken this class, I'm going to go to Wikipedia and find myself a reasonably fast algorithm. So Pat goes into Wikipedia and say, well, I remember from college, somebody mentioned the easiest search algorithm is called linear search. Okay, so we look up linear search in Wikipedia, and it has this part here. See, Pat does not want to even read about all this stuff here. Sounds too theoretical and stuff like that. See, Pat is this guy here, right? So he looks at all this stuff here. It's like, wow, too many symbols, too much math. Skip. Oh, here's the search algorithm. Let's see here. Okay, 6 lines. I can deal with that. No problem. Whereas me, after taking a class, see, I'll be this guy here, writing, kind of frantically on my notebook. Actually, I'm the one who's dozing off in class most of the time. Just because, I have, too much homework assignment to do and whatnot. But I tend to, absorb the stuff anyway in my classes. So I go to Wikipedia and I go to other resources and try to find the most efficient way to search for something. Okay, in fact, you can probably just search it here. You can say, most. Come on.
But you can try. But the 486 isn't exactly the best.
Most efficient search algorithm. Ooh, somebody apparently has done it already, and it's binary search. So I click on binary search, I read through all this stuff here, I understand the big O notation, I know what is log, and so on and so forth, and I look at the algorithm, okay, which is right here. This is actually kind of written in C already. I think it's a recursive version. No, it's not recursive. But anyway, this is the binary search. Pat kind of took a peek at my algorithm, go like, you started off with a computer that is really, really slow compared to mine, and you want to use a long algorithm like this? Are you crazy? I go like, well, let's give it a try, okay? Okay, so now we have this competition. I am using binary search, and Pat is using linear search, okay? So now we use a spreadsheet to take a look at, what's going to happen next, okay? I like spreadsheets because, they're just a big, huge calculator. All right, so the first column, bar A, is representing bar A bar, which is the size of the array, okay? Because the boss will basically say, okay, give me an answer, is this item in this array, okay? And the array size is bar A bar. This column represents how much, the unit of time I need to finish the algorithm, to come up with a conclusion. Is it there or not? And this column will represent how much time Pat's computer will need in order to perform the same operation. I have my algorithm, Pat uses a different algorithm. when the problem size is 1, in other words, we have a trivial array of only one item in it. How many comparisons do you think binary search needs in order to confirm is that the item that we are looking for? One. Okay, that makes sense. Okay, so I would need 1 unit of time. Pat's computer, being super duper fast, is going to say, okay, I need this much time, but you know what? Because my computer is so much faster, I'm going to divide it by 65536, which is 2 to the power of 16, and we'll divide it by 2 because it is a sorted array, and we will incorporate the optimization that we were talking about a little bit earlier in this class. So Pat's computer will take that much time relative to my 1 unit of time to finish the algorithm. Okay, so that's 7.6 times 10 to the power of negative 6 compared to 1 unit of my time. Okay, all right, and we'll probably we want to reformat this cell to use a more obvious notation. So we have, okay, that would be good. Okay, so that makes it more clear of what kind of magnitude we are talking about here. And obviously my boss needs a really fast hand to clock it. And Pat is saying, oh, okay, Tech, you want to do a rematch? Are you ready for more embarrassment? And I say, yeah, why not, If I'm leaving, why would I worry about embarrassment in this company? Okay, with 3 items in the array, how many comparisons do I need using binary search? Well, let's think about it. Okay, with 1 item, I need 1 comparison, right?
Yeah.
With 3 items, I would use the first comparison to compare with the middle one. Then I only have 1 left,
So
right?
that
Either the
means
top
you only-
half or the bottom half. So that means I only need 2 comparisons to handle an array of 3 items. Is that making any sense?
Yeah.
Okay. So in my case, I'll just say that, well, compared to last time, I will need 1 comparison more than that. Just like that. Pat's computer, or Pat's algorithm, is proportional to the size of the array. So in this case, it is basically, if you look at the equation, it is A3, which is this cell, divided by 2, because we are using the optimization of sorted arrays, and divided by 65536 because of the speed difference of the computers. Are we doing okay so far with the assumption and why the numbers turn out the way it is? If you look at the net difference between these 2 numbers and the net difference between these 2 numbers, Pat is gaining on me. Okay, the difference is bigger. All right, but I'm ready for more embarrassment, so we'll say, okay, let's make it 7 items. Now, why do I pick 7 items? 7 items, I pick 7 items because 7 items is 2 times 3 plus 1. In other words, with 1 single comparison, I can take out, I can basically have only 3 items left. But I already know with 3 items, I only need 2 comparisons. So that means with 7 items, I only need 3 comparisons. Okay? All right. Now, since I'm lazy, I can do it like this. And Pat's computer, or the time that Pat needs to finish his algorithm, or her algorithm, is that much time. Okay. What would be the next number that you think I'm gonna go for?
10.
7 times 2 plus 1. Because I would end up with 7 here, plus something in between. 7 plus 7 plus 1. So the general equation is whatever I had before times 2 plus 1. Okay? And I will need 4 comparisons in that case. And Pat's computer will take that much time to finish the same thing. Okay, to come up with a conclusion, is the key in the array. Okay, so we'll basically look at this and go like, well, Tech is not ready to give up, but I got time, so we'll keep going. All right. So up to this point, you can see that hey, I'm not. It doesn't seem like I'm gaining in any way. If you look at the net difference between my column and Pat's column, if you look at the difference is actually increasing for, up to here. Okay, we are dealing with an array of 2,047 items at this point. Okay. And Pat is saying, well, we can do this all day long. I don't think you're going anywhere. And then my reply was, but I think you are going somewhere. You better start packing now. Pat is just laughing. So we keep going. And Pat is saying, yeah, but I don't see anything happening yet. All right. Oh, okay. So at this point, Pat's computer is taking close to 1 second to search in, well, I would say that's about 131,000 items in the array. My algorithm is still really slow by comparison. It's taking 17 seconds. But you can see that, hey, it's starting to look a little strange now because, the lead is no longer continuing. Okay, if you look at the net difference, this is when it starts to level out. The next item, I think Pat is starting to panic a little bit here. Maybe a little more. Starting to cry. Starting to scream.
Oh.
And right now, Pat is saying it's not fair. It's just not fair that Tech is using a 486 computer. We need to downgrade it to a 386 computer. We need to downgrade it not to a 386, but a 386SX computer. Okay, now this is way before your time. The 386 computer is a 32-bit processor, which means it has a 32-bit data bus. The 386SX processor is basically internally the same as a 386 computer, but externally it has a 16-bit data bus so that the circuit board is easier to make. But that also means it's a lot slower because it will take 2 cycles to write out a 32-bit integer instead of 1. Okay, but do you think that's going to help? Downgrading my computer to a 386? It will only defer the inevitable, right? So that is why, the efficiency of an algorithm is actually important, okay? Because for small search cases, for small arrays, it doesn't seem to make any difference. But as soon as your array starts to become larger and larger and larger, a good, efficient algorithm makes a huge difference in terms of how much time it takes to execute. You can have the fastest, the most, powerful processor, but if the algorithm that you're picking is not efficient, that means, when the problem scales up, the amount of time that it takes for your computer to solve the problem is no longer dependent much on the raw speed of the processor. It becomes more dependent on the algorithm itself. How well does it scale up in that case? Are we doing okay so far with these concepts? This is called time complexity, by the way. Okay? The problem is not with the speed of the computer. The problem has to do with the curve. How much time does it take relative to the size of the problem? So if you plot, time versus, the size of the problem, which I use, bar A bar to represent, linear search has a linear curve. The larger the problem, the more time it takes, but it has a linear relationship. You double the size of the problem, you double the amount of time it takes to solve the problem. Binary search has a logarithmic curve. Okay? You double the size of the problem, you only add 1 to the number of comparisons. So if you just stretch out the curve part, the log curve, you're only going to change when the intercept happens. It will happen eventually. Is that making any sense? So that's why this kind of theoretical stuff is actually important. And I firmly believe that in some commercial software, the developer originally only had very small documents to test, the software. So that's why, when you have a larger document, the time it takes to update the document is not proportional to the size of the document itself. Now, what I'm talking about is, when I wrote my dissertation at UC Davis, it was only about 90 pages, so it's not really long to begin with. but I do have a lot of references. Okay, so this is referring to that section, this is referring to that section, and so on. And after I got past about 60 or 70 pages, Microsoft Word 2.0 at the time just came to a crawl. It just suddenly started to slow down to the point where, hey, what is happening here? I mean, nothing seems to be happening. And then 15 minutes later, the document is ready. Finishing, it would finish updating itself, updating all the indexes and whatnot. And I think it's a problem with this sort of thing. Somehow the algorithm that they picked to use does not scale up with the size of the problem. Okay. Now there are really, really bad problems too. You can use this to your advantage as well to keep your job. So what I'll do next, over the next 6 minutes or so, we'll be using another example to illustrate why time complexity is important and why it is important for you to understand, what it means and when to use it, to argue that, hey, it's not my problem. Okay, because it will happen. Let's think about pizza delivery. Okay, so we're switching from this context to pizza delivery. How many stops do you think would be typical for a pizza delivery truck, car, whatever? Sorry?
4 to 5, 3.
4 to 5. Okay, so let's say it's 5. Okay, so with 5 points in a route, how do you optimize the route to deliver delivery to 5 places? Let's say they're all within the same neighborhood, so it's not like one is over here, one is over here, and it's clear how to traverse the 5 points. So let's say all 5 points are okay. Let's say this is the pizza shop here, and we have 5 points that are kind of all around the pizza shop itself. So it's not really clear cut. It's not like the pizza shop is here. The 5 points are arranged kind of like this, where you can say, oh, okay, we can just traverse it like this. It's kind of like all over the place, and you can't really easily tell, okay, we can go here and then here, and that would be the best path. But we can evaluate every single possible way to combine the paths, right? In other words, if you have 5 paths, you can say, okay, A, B, C, D, E, okay, C, D, E are my alternatives for the first point of delivery. After you pick the first one, how many choices do you have for the second choice?
4.
There are only 4 left. And then you have 3 left, 2 left. After you have picked the first 4 delivery points, the last one has to be whatever is remaining. So that means, with 5 delivery points, how many combinations, how many ways do we have for traversing those 5 particular points? 5 times 4 times 3 times 2 times 1, which is 120. Okay? So there are 120 ways to write A, B, C, D, E in different orders, different permutations of 1 to A, B, C, D, E. So once you have 120 possible routes, you can just do a time calculation or plug it into a Google API to find out the time estimate. Whichever combination comes up with the best time is the one that you can take. Pretty easy thing to optimize, okay? Because you only have 120 possible routes, and it doesn't take much time to evaluate all 120 routes. So let's say you work for a pizza company and you say, okay, let me show you an app that I can do, and your boss is totally impressed, right? So instead of delivering pizza, your boss is giving you a different job. Now you can start to write apps and stuff like that for the pizza shop. And then one day your boss called you into the office and say, you know what, Tech, you are fired. You are so fired. And I go like, what? What did I do? That program that you wrote for pizza delivery doesn't work. I go like, what do you mean by it doesn't work? It has been working for the past few months. In fact, we saved gas and time, and stuff like that. You saved money. Why are you firing me? And the boss said, you know what? I saw that it was working so well for us that I sold this program to my buddy, who operates a package delivery company. And go like, okay, so what happened then? It doesn't work for that company. My buddy is now suing me for selling him something that does not work. Go like, it's working fine, so why is it not working? my boss said, well, you know what, I think you're just a bad programmer. I'm gonna hire the next person to fix this problem. And then suddenly I remember something. I remember the problem that we were just talking about is also called a traveling salesman problem. Now with the traveling salesman problem, it is known to be a hard problem to solve. What do you mean by hard problem to solve? I mean, we have solved this problem many, many times already over the past few months. How many stops do you think a package delivery truck has to stop? How many points?
A lot.
Well, just give me an order of magnitude.
35.
Let's say 35. Okay. So with 35 points to drop off, how many combinations are we talking about?
Too much.
Okay, 35 versus 5 doesn't seem like a big deal. 7 times, okay, big deal. It's not 7 times. Because we're talking about 35 factorial versus 5 factorial. What is 35 factorial, by the way?
34, 33, 32, all the way down to 1.
Yep, well, since I'm in a spreadsheet already, we'll just go ahead and use a spreadsheet to do this calculation. So I think it's either factorial or just fact. Yep. The 35 factorial is this number. It's 10 to the power of 40. Okay, so 10 to the power of 40 compared to 120 here. No wonder that program doesn't seem to be working, right? Because there's just a whole lot more to consider when we have 35 drop-off points. Now, at one point of teaching this class, I actually had a student who worked for, I think, either UPS or FedEx, and he said the typical number of stops, for a UPS truck is 100.
No.
Okay, and you're thinking 100 versus 35, so maybe we are just tripling that number. Not quite. Okay, so let's take a look at the factorial of 100.
Oh my god.
So it's close to 10 to the power of 158. Okay? So no wonder that program doesn't seem to be working. But the biggest question is, will my boss be able to find someone who can solve that problem much more efficiently? Well, if you read up on NP completeness and stuff like that, which are completely theoretical, basically bringing us back to that comic strip, the cartoon thing, that will bring us back to this picture here. Okay, because the same class, okay, will talk about this problem being intractable. It is a very tough problem to solve, and up to this point in the entire history of computer science, 70-something years, no one has ever come up with a solution to that particular problem. It's called NP complete. It is a tough problem to solve. Okay, so knowing that, you can argue with your boss and say, this problem, the nature of this problem is that tough to solve. Okay, there's no way anyone can solve that problem. Whoever can solve that problem is not going to work for you. Okay, so that's why this theoretical stuff is useful, because you can identify the difficulty of a problem ahead of time, and you can basically say there is a solution, but you're not going to like it. It's not going to be practical. And just solve right there, and just say that cannot be done. Okay, so I'll see you guys next Tuesday. Have a nice weekend.
Doesn't look like it.